Thank you, Marco. So this class will be really about well, mostly about galaxies, but a lot of the stuff we're going to discuss will apply to other tracers as well, and it will be heavily based on the material that Julien presented. So thank you, Julien, for all the providing the background. So the general story of structure formation is that we have linear dark matter fluctuations that grow during matter domination, and then they collapse on small scales where the density fluctuations become order 1. They form dark matter halos, and then galaxies form baryons. They interact with radiation, they radiate, they cool down, they condense, they form galaxies inside the halos. So this is the basic picture of galaxies that we get to see in galaxy surveys. And obviously, galaxies are extremely nonlinear, right? We're sitting inside the galaxy. If you look out at what is going on, you will see a lot of complicated physics going on: stars, gas, magnetic fields, cosmic rays. So there is absolutely zero hope to understand this from first principles. But however, not all is lost. And actually, there are some properties of galaxies, specifically their properties as an ensemble, as a distribution on large scales. And in this regime, we can predict the certain observables involving galaxies very, very accurately, even without knowing in detail the galaxy formation physics. And so this is the content of cosmological nonlinear perturbation theory that is also known as the effective field theory of large-scale structure. In my lectures, I will not be distinguishing between, perturbation theory and EFT. I know that some people do this distinction, so for me it's the same. So to start off, let me, first introduce the EFT ideology that will really help us understand what is going on in this picture. So, okay, I have chapters and paragraphs just to make it a little bit more structured. Okay, it's chapter 1, EFT ideology. Okay, EFT, effective field theory ideas, are a cornerstone of theoretical physics. In fact, they appear in many different physical systems. So in condensed matter, particle physics, obviously, fluid dynamics, etc. And EFT hardliners even think that, even tell you that the reason we are able to do physics is because of the EFT, is because of the scale separations that is happening here. So the key principles of EFT is the simplicity principle. Simplicity principle. So on large scales, okay, so typical situation is that we have we have a system that on some scale is very complicated, just like our galaxy. So there are a bunch of, particles or more complicated objects at a certain scale where things are difficult. So there is some length scale associated with this that I'm going to call L difficulty. And then on scales larger, much larger than the scale of difficulty, a simplified picture emerges. And basically, this pretty much sums up the principle of simplicity, that on large scales, for system like that, on large scales, the dynamics simplifies and it can be described by a few, so by a small amount of dynamical variables that we call degrees of freedom. And symmetries. So in this regime, the properties of small-scale dynamics are described also by a finite number of parameters, constants. So whatever is going on here will have a limited impact on this, and this impact will be captured by a few parameters. And your final answer on large scales will be function of the scale separation, so L difficulty divided by the scale you're looking at, scale of interest, L. And this function is analytic in the limit L difficulty over L going to 0. All right, so this is the key principle of AFT. So this is some sort of, ideology. It's not the theorem. There are obviously systems where, things like this don't happen. Or for instance, if you need to take a look at really small scales, you cannot apply this logic anymore. But for a lot of systems and physics, this logic holds true. And just to give you a few examples that will be relevant in our context. Okay, let me start with the first example that everyone is super familiar with, which is the multiple expansion in electrostatics. Well, I'm writing E&M, but really it's electrostatics. Okay, so we have some complicated charge distribution. So this could be something, really difficult, like for instance, in QCD, there are a lot of states whose, content we don't know, like for instance, sigma meson, we don't really know what it's made of. So there is some complicated distribution of particles here, and this distribution has a typical scale, extent that I'm going to call A. And then we want to compute the gravitational, well, here in this case, the electrostatic potential produced distances much greater than the size of the charge distribution. So we know from electrostatics that our answer on very large distances will be given just by the charge divided by the distance. And then if we get a little closer, we start feeling other multiple moments. So the next correction will be given by the dipole. So n here is the unit direction vector. And then if we get even closer, we start feeling higher order multiple moments, like for instance, the quadrupole, etc. And oh, okay, let me write down the definition for this thing. So charge, obviously just the integral over the charge density, and then dipole moment is the same integral weighted with the coordinate. And the quadrupole, again, will look quite similarly. It will be just a slightly different weight. Okay, so from this description, we can see, well, we can estimate how different terms scale in the multiple expansion. And here we know that this is the charge. We can just estimate by order of magnitude what the dipole is. So by order of magnitude is charge times the size of the charge distribution, right? Because this integral is non-zero only for this tiny region, okay? So we'll have A, quadrupole will scale like Q times A squared. So now we can write down our multiple expansion in terms of a simple Taylor series. And indeed, you can see that our answer organizes itself as an analytic function in terms of A over R, okay? And this expansion involves only a few parameters. So charge obviously is only one parameter, right? So on very large distances, doesn't matter how complicated the distribution of your particles is, a single parameter that gives you the answer, which is the charge. Then when your sensitivity increases and you start being sensitive to next to leading order corrections, you have the dipole, which gives you the 3 parameters. And then at the next to leading order, you get the quadrupole, which has how many parameters? Who knows how many 3 parameters does a quadrupole have? Yes, 5. Brilliant. Yeah. Can you explain why? Right. So yeah, just in other words, it's symmetric and trace-free. So symmetric will have 6. Trace-free, you subtract the trace. As you can see, you get 5. All right. So you see that regardless of how difficult, and this expansion is true for any charge distribution, right? It's true for sigma meson, for proton, for anything you would want to think of. So regardless of the microscopic, let's say, dynamics, microscopic properties, you only have finite number of parameters for any system. Okay, now let's discuss a different example that now will be very relevant to what we're going to talk about. So another canonical example of an effective field theory, which is the Navier-Stokes equation. So example number 2. Navier-Stokes equation. Or fluid, let's say fluid dynamics in general. Again, the typical story is canonical for an effective field theory. We have on small scale, so on a scale of the order of the mean 3 path, which as we know scales like 1 over sigma and bar and v, cross-section of interaction between particles, number density, and the mean velocity. So we know that the dynamics is complicated, right? So we have a bunch of particles, for instance, in the water, that interact by virtue of some electromagnetic forces, often, most of the time, coupled with quantum mechanics, like, for instance, van der Waals forces. You can only understand quantum mechanically. Okay, so there is some complicated distribution of particles with complicated interactions. However, on scales larger than L mean 3 path, we can introduce coarse-grained fields, which are our degrees of freedom. The density field, the velocity field, and the pressure field. Well, in our case, I'm going to assume right away that there is some equation of state, so there is some speed of sound. All right, so we introduce these fields, and then we can write down the equations of motion for these fields that are based basically only on the symmetries. And the first relevant symmetry is the mass conservation, which gives us the continuity equation. And then we have the momentum, well, I don't want to say conservation, but let's say momentum exchange or momentum dynamics equation, which is in a perfect fluid case would be just the earlier equation. Well, now it will have additional terms. So we'll have this beautiful material derivative. And then on the right-hand side, we'll have the gradient of the pressure. And then the viscosity terms, we'll have the shear viscosity. And we'll have the bulk viscosity. Okay. So the most interesting equation here is this one, the Navier-Stokes equation itself. So let me label different terms in this equation. 1, 2, 3, 4, 5. And let me now play a similar game and try to estimate how important these terms are. All right, so dimensional analysis. So let's assume that there is a let's say, equilibrium configuration of our fluid with some average density, rho naught. Then for the velocity, well, we know that the typical velocity of propagation of things, signals, in the fluid is the speed of sound. So we can say that by order of magnitude, v scales like the speed of sound. And then we're also going to look at this equation in the Fourier representation. So we're looking for a typical solution. It looks like waves, so fluid waves. So from this, we can also, if we ignore these things, we are going to find a solution that describes the usual fluid waves with the dispersion relation omega equal CSK. So we have a relationship between the gradients and the typical time derivatives in the system. So let's estimate different terms. So the first term with the time derivative of the velocity field will scale like rho naught times omega times cs. Okay, this is very clearly rho naught k cs squared. Now we can play the same game for the second term, v nabla v rho naught cs squared. So you see that they scale similarly. Okay, let me use maybe this little amount of space here to estimate the third term, the pressure term. So P, okay, dP will scale like CS square rho naught, and we have the gradient that also scales like K. All right, so 1, 2, 3 scale the same. Now, the viscosity terms, well, both of them are going to scale like this. So they have some parameter, viscosity, and they have some sort of second derivative of the velocity field. So it has a k squared times cs. So now we can do the following. We can single out the combination that we had before, and the rest put in a separate combination. So you can see that the viscosity terms that are smaller, right? So all these three terms, 1, 2, 3. Okay, sorry, 1, 2, 3 are here, right? So they scale like k times cs squared times rho naught. The viscosity terms scale like the perfect fluid terms times an extra gradient, right? And then the scale that appears here that you need to introduce basically by dimensional analysis to make up the dimensions. So this is precisely something that gives you the mean free path. So as long as the typical wave numbers you're looking at are small, so the wavelengths are big compared to a mean free path, this is a tiny number, right? So in general, it's a small correction. So you can say that 1, 2, and 3, they roughly scale the same, and they're much greater than 4 and 5. So in this sense, you can rewrite, well, you can see that basically the Euler equation, Navier-Stokes equation that you have, organizes itself in a way very similar to the multiple expansion that we had before. So it has a leading order term, leading order part that scales like rho naught cs squared k, and a subleading part that scales like rho naught cs squared times k times mean free path. All right. So in some sense, now this is our monopole, this is our dipole, okay? And then in principle, there could be higher order terms in this expansion. Yeah. in principle, yeah, these other higher order terms, well, we don't normally discuss them, but they appear in certain contexts, and there are like ways to proceed and build, how to build more things on the right-hand side that appear either in the context of heavy ions or ADS-CFT correspondence. But in general, we know that those things are just the first terms in the Taylor series that appears, right? Just like the multiple expansion, in principle, it has an infinite number of terms. Also, the fluid equation here on the right-hand side has an infinite number of terms, okay? But these terms are small. And in this sense, at this point, we can also kind of get the idea that the terms that we're writing down here on the right-hand side are the only terms that you could write down. So in this sense, it is fair to say that the fluid dynamics is severely constrained by the symmetries, because the Navier-Stokes equation we can just rewrite in this form, where we have the material derivative, capital D, and then, well, we have on the right-hand side, in general, the derivative of the stress energy tensor. And now for the stress energy tensor, we are writing down a gradient expansion, right? That is consistent with symmetries. And the leading order term that you could write down, okay, so it has to be a tensor under the SO3 indices, right? So the leading order term that you could write down is going to be a delta function times, well, something, right? That doesn't have any gradients. And this is your pressure term, right? Typically, the convention is that we're writing this down with the minus sign. And then you would want to write down terms that involve gradients, right? And in general, you would want to use the velocity field, and there will be only two terms consistent with the symmetries that you could write down at leading order. So only two operators. So either you can take the divergence of the velocity field and multiply it by the Kronecker delta, or you sort of write down something like this, plus symmetric combination, right? With some general coefficients, C1, C2. And you cannot write down, you can see that, okay, based on the symmetries, these are the only terms that you can write down. So for instance, you cannot write down a term that would look like this, VI, Vj. Who knows the reason why you cannot write down this term here? Think about the building we're standing in. It's named after who? Come on, guys, the building. Galilean invariance, perfect, right. So if you have a gradient, then you see that you can shift the velocity field and it's not going to change the energy momentum tensor, right? Stress tensor. So now this is not going to be Galilean invariant. So you cannot write down these things. But, right. And also, I mean, I already mentioned that, okay, you need to respect rotations. So there's a second symmetry that you have. So all these things, they should transform under some fixed representations of rotation, right? So in other words, if we have two indices, or plainly speaking, that everything here on the right should have two Euclidean indices as well, okay? So this way we respect both symmetries, Galilean invariance and rotational symmetry. Okay, so the Navier-Stokes equation is another canonical example of an effective field theory where symmetries constrain the dynamics. And well, the two concepts that are typically mentioned when we talk about the fluid equation, again, is simplicity, right? So we have an amazing equation that describes the dynamics of any kind of fluid with only three parameters, right? So three parameters. We'll have the sound speed here. Three parameters describe any fluid. And the concept that is related to this, where we reverse the arrow, is called the universality. So the universality is the statement that any fluid can be described by three parameters. Well, for instance, so let's say the air in this room is described by the Navier-Stokes equation and tar is described in Navier-Stokes equation. Obviously, microscopically, tar and air are completely different, right? Yet, on very large scales, the simplicity principle happens. So we have a simplified dynamics where there is absolutely no difference in terms of the equation. And the only thing that allows you to distinguish between air and tar are the values of the coefficients that appear. Okay? All right. Are there any questions at this point? Yes. This is. Oh, this is fine. What you want to do here is you want to make your theory invariant with respect to the change of the frame, right? So it's true that the fluid itself, it has okay, there is a frame associated with this, right? But in principle, you would want to have a description valid in other frames as well, right? So for the fluid dynamics to make sense, regardless of the frame, you need to write down this. Because if you write down something like this, you would have different effects in different frames, right? Okay. Any other questions? All right, very good. Now we are ready to move towards cosmology more closely. And now we're going to something that I call chapter 2. Okay. We're going to recap some basic stuff about the formation of structure in linear cosmological perturbation theory. Okay. So chapter 2. Facts about linear cosmology. That everyone here needs to know. Okay. The central object that we're going to discuss is going to be the matter power spectrum. Yeah, this will make sense even when we move to galaxies, because dark matter forms a backbone of structure formation. So galaxies form kind of on the background of matter. So that's why matter power spectrum is key even when we talk about tracers. Okay. So what is matter? Well, typically when we talk about matter, we really mean the distribution of matter fluctuations. So we talk about the density contrast, which is a statistical field that satisfies fluid equations. Now, in the context of galaxies, a little remark is that we'll be dealing with the galaxy overdensity field that is defined with respect to the number density. Okay. But again, from the point of view of our discussion, those are just some fields. These fields don't have position space, they don't have any dimensions. So there is no big difference between dark matter and galaxies. Okay, so these are random stochastic fields, which means that their particular realization that we get to observe in our universe doesn't carry much information because we only get to observe one universe. So what makes sense is to look at their correlation functions. And the simplest one is the two-point function in position space, which measures how much the overdensity of matter is correlated across distances. So typically, we look at the two patches of the sky separated by some distance r. And thanks to the cosmological principle, we know that the two-point function is going to be a function of the module of the radius vector only. And oftentimes we'll be working in terms of the Fourier representation. form our galaxy density field. And then we can also compute, so knowing the two-point function, we can compute the two-point function now of the Fourier image of delta, and this will just give us the usual power spectrum. It was already discussed here many times, so I assume that everyone is familiar with these things. Now, thing that will simplify notations a lot will be the use of the primed correlators, where prime means that I'm going to strip off the 2 pi cubed and the delta function. So the primed correlators, just the power spectrum itself. Okay. All right. And obviously the correlation function is a three-dimensional inverse Fourier transform of the power spectrum, which, since the power spectrum only depend on the module of the wave number, of the wave vector, so only wave number. So this will boil down to a simple one-dimensional integral that only involve k, and the weight will be sine kr over kr, which is the usual spherical Bessel function of the zeroth order. So this is just the usual kind of Fourier transform of spherical quantities in 3 dimension. Okay, now let's talk about linear perturbations. So everything starts with the linear growth. Linear perturbations. Okay. So in linear theory that Julien nicely already covered, we know that during the matter domination, the density contrast grows, and this growth, well, basically at matter, during matter domination grows with the scale factor, but then because of the cosmological constant, this growth becomes slightly different. But the general statement is that the entire evolution of matter fluctuations in the universe in linear theory does not change the wave number, right? It does not affect the phase, in other words, right? It's only the evolution here. So all the time dependence basically is absorbed, all the evolution is just encapsulated entirely by the growth factor. And so in linear perturbation theory, delta 1 is much smaller than 1 for linear perturbation theory to make sense. Well, we will see shortly what happens to this as the structure formation develops. But in general, this nice factorization that in linear theory we don't have any change to the phase of the field, well, basically means that the shape of the power spectrum will remain unchanged. And the only thing that changes is the amplitude of the matter power spectrum. So typically the matter power spectrum, P of k, here I call it P11 of k, it has the following shape. So it goes like k for low wave numbers, and then it has a turnover for k around k equality, 10 to minus 2 h over megaparsec, and then goes down. And asymptotically, it goes down like k to the minus 3 times log of k times k over k equality squared. And this log is something that gets imprinted because of the growth of dark matter fluctuations during the radiation domination. And here there are some baryon acoustic oscillations. So this is the typical matter power spectrum at redshift 0. And then because of this factorization of the time evolution, if we want to get the linear matter power spectrum at higher redshifts, well, for instance, at redshift let's say 1100, where recombination happened, and after that, baryons and dark matter started behaving more or less like a single fluid. So the power spectrum at this redshift, where, well, we can say that the nonlinear structure formation really begins. So it's given by the exact same power spectrum. It has the exact same shape, but just the amplitude is smaller. So it's down by the square of the growth factor. Typically, the convention is that we define this growth factor such that it has amplitude equal 1 at redshift 0, and then it's smaller at higher redshifts. All right. Are there any questions here at this point? All right, very good. So more about the growth factor. So as I mentioned, during the matter domination, when, well, basically we can ignore all components except for the density of matter. The growth factor is just given by scale factor. It's 1 over 1 plus z. However, we know that we don't live in a matter-dominated universe right now, so we're living in a lambda-dominated universe. So it makes sense to account for this fact. So for actual lambda CDM, the relevant parameter that is going to be important in our discussion is the abundance of matter as a function of redshift. So normally, we're used to seeing omega matter without z, but in the context of large-scale structure, it makes sense to define omega matter as a function of z, which will be basically the abundance at a redshift z as follows from the Friedman equation. So the usual omega matter and omega lambda from the, let's say, Planck cosmological parameter papers, I'm going to call omega matter naught. So naught is for redshift 0. And you can see that in general, this is something that by definition at higher redshifts, well, it will approach 1, but it's always going to be less than 1. And especially it's going to be less than 1 at low redshifts, right? Where we know that its value at redshift 0 is 0.3, roughly. Now we can solve the linear equations for the linear dark matter fluctuations, and we're going to find the growth factor. So we're going to find something that, okay, very roughly will look like this. So if I multiply the actual growth factor by 1 plus z at high redshifts, I'm going to find a constant. At low redshift, it will be, well, something less than 1. And by the way, here I'm going to let you guess where 1 is. So at some point in the asymptotes. And I'm going to ask you, how many of you think that this value is 1? So who thinks that this is 1? All right, nobody thinks that this is 1. You think that this is 1? Okay, good. Who thinks it's greater than 1? Okay, who thinks that it's smaller than 1? So here I'm going to use this, right? I'm going to say that d plus of 0 is 1, and also a of 0 is 1, okay? So these are two facts. But in one case I have dark energy, in another case I don't have dark energy, okay? So if I normalize these two things to the same value at redshift 0, which one is going to change more? All right, I'm going to write down that the actual value is 1.25. And I'm going to, I'll let you think a little bit why is that the case. But really just follows from these two facts. Okay, so if by the end of the lecture it's still unclear, you can then ask me maybe after the lecture. Okay, so I'll let you guessing. Another important quantity that you often see in the literature is called the logarithmic growth factor. Okay, so I'm running out of space here. So F is d log d plus over d log a. Again, it's a function that is 1 for a matter domination, and then it's something that is less than 1 for lambda domination. Now, this function looks much better because it really does approach 1, f. And then its asymptotic value, well, at ratio 0, its value at ratio 0 is around 0.5, roughly. Okay, this is something that measures the departures of the growth factor away from the scale factor. Okay. Now, already from linear theory, we can extract some information about, the nonlinear structure formation. Some relevant numbers that play a role already in the regime where dark matter fluctuations become nonlinear. One of such quantities is called the dimensionless power spectrum. Okay, let me say that this is the new paragraph. Useful quantities. Okay, this is the definition of the dimensionless power spectrum. It's the usual power spectrum times k cubed over 2 pi squared. Okay, this seems like a very strange definition. To really understand what is going on, let us compute the variance. Let us compute the variance of the density field at the same point, right? So since we know that, well, we have already discussed the definition of the two-point function. We know this definition, so this just computes the correlation function at 0 separation, right? So now I can just copy these expressions above, and since the separation is 0, I can completely ignore the exponent in my Fourier transforms, right? So I'm going to get an integral over the entire k range of my power spectrum that will precisely look like this. So you can already see the 2 pi and k squared appearing. If I change the integration variable to log k, I'm going to find precisely my linear, well, I guess this definition is true also for nonlinear. I'm going to find precisely my dimensionless power spectrum. So now you can see what's its physical meaning. So the dimensionless power spectrum measures the contribution of a range of modes around k to the total variance of the density field in position space. Okay. Oh, thank you. Thank you. Right. All right. And okay, so for instance, when the density fluctuations become order 1, where linear theory breaks down, you can see that this precisely corresponds to the fact, to the, to the range of momenta where this becomes order 1. That gives us another useful quantity called the nonlinear scale. So also known as scale where perturbation theory breaks down. So this is the momentum for which the dimensionless power spectrum becomes order 1, or strictly speaking, exactly 1. This is how it's defined. So that means that the modes with the wave number k nonlinear, they have exactly order 1 density fluctuations. Okay. Just to give you some numbers in the context of the usual lambda CDM, let's say Planck best fit lambda CDM model, for Planck lambda CDM at redshift 0, k nonlinear is roughly 0.3 h over megaparsec. Now, another useful quantity is an approximation to the actual power spectrum called the power law approximation, or in this case, we say that we talk about the power law universe. So power law universe approximation. Okay, this is really very simple. So from this discussion, okay, you can see that you can kind of think about the power spectrum as a collection of modes, some ranges of modes, each contributing some amount of power in position space, right? And we have this power spectrum in linear theory that in principle can be computed for any k, but then for actual galaxy surveys, since the universe is finite, the sky is finite, we only get access to a limited range of scales around this, ranging, well, roughly from, let's say, 10 to minus 2 to, let's say, 0.5 h/r megaparsec. So in this limited range of scales, the total power spectrum could be approximated like a power law. Well, specifically for the BEO scales, where we know a lot of information is coming from, BEO are happening on a very small range of scales. So the power spectrum, it's kind of de-wiggled part, smooth part, can be all approximated as a power law, k to the n. So that's why there is a very useful way to think about these things, at least for quantitative estimates, to approximate the matter power spectrum with a single power law. And as you can see from this discussion, this is something that is going to be accurate for the range of scales that are interesting for us. So I'm going to define this power spectrum like that. And in this case, you can see that P11 at k nonlinear will be exactly 1 by construction. And for the actual lambda CDM universe, preferred by Planck, the spectral tilt is close to minus 1.5 for k around 0.1 h/r megaparsec. So this is the range of scales relevant for the BEO. And k nonlinear, as before, is 0.3 h/r megaparsec at redshift 0. So clearly, k nonlinear is something that depends on the redshift, right? So this is roughly where the power spectrum becomes order 1, but the amplitude of the power spectrum goes down. So that means that we can go to smaller and smaller scales. Well, you need to multiply by this by k cubed. In this sense, the power spectrum will always look like this. And at higher redshifts, it will be just like going down the dimensionless power spectrum. So because of that, the nonlinear scale moves to higher and higher wave numbers. All right. Power law approximation. Okay. Couple of other related quantities. Mass variance. Okay, mass variance is really a simple quantity. We've already encountered this before. So this is the two-point function of the density field at 0 separation. So two-point function evaluated at 0. We already have this expression above. Now, what's interesting about this expression is that if I take the prediction of a linear matter power spectrum, let's say that matches Planck lambda CDM best fit, and I plug it here in this integral, it's going to diverge. So it's going to diverge, which obviously makes sense because we need to cut it off. And we need to cut it off because we can trust linear theory only up to k nonlinear, right? After k nonlinear, the modes that are higher than k nonlinear are all nonlinear. So we cannot use the linear theory prediction for them. So that means that this integral, we can evaluate only up to k nonlinear, or let's say up to a scale around k nonlinear. And that, in this case, the mass variance will be finite. A more systematic way to deal with these difficulties associated with the divergence of the mass variance is to introduce some smoothing. Well, typically, we're going to smooth our density field at some position x. We're going to smooth it with a top hat window function in position space. So we're going to introduce this top hat filter. H is the Heaviside function. And in this case, the filtered density variance now will be a convolution. So it'll be a convolution with this filter, right? So basically we'll tell you that we're going to cut out we're going to cut out the region that is kind of outside of the sphere. And in Fourier space, this will be a simple multiplication of the Fourier density field, well, times the Fourier image of the top hat, which is given by a spherical Bessel function of the first kind, which again is just some bunch of sines and cosines. But the point is that now this density variance of the smoothed field is going to be finite because the unwanted large K behavior is going to be cut off by the filter. And one important fact to keep in mind here is that the integrand of this expression, integrand peaks at k equal pi over 2r, which is roughly 1.2 over r. Okay. So this definition also, the smoothing also gives us a nice conversion formula between the position space and Fourier space. You see that, there's always a discussion whether there should be 2 pi or not 2 pi. So the actual answer is this, pi over 2. Have a question? Yeah, okay. Right. It's just a convention. In principle, the idea, right, is that you can smooth your density field with any kernel, and any uncertainty associated with the arbitrariness of your choice will be absorbed by some EFT parameters, meta parameters that you have. So in the end, it doesn't matter. At this point, it's just important to regularize it somehow, okay? And historically, this was a very nice, simple way to do that. It's ultimately, okay, I can tell you, historically, it also has to do with the fact that people wanted to, have a spherical something, a spherical quantity, for which you can use the spherical collapse model, which is an exactly solvable model for structure formation, okay? So this is how it was motivated originally, but right, you're completely right. In practice, we don't have to smooth with a particular, function. You can use other functions as well. Oh yeah, right. So this exactly, yeah. There's no yeah. Okay. But will be exactly 1 over r or 1.1, 1 over r. Okay, so you see the only difference whether you have 1 or 1.2 here. Okay. Here we go. Okay. The final quantity that, okay, we will need to get some idea about structure formation is the displacement of dark matter particles. Okay, so the displacement is a key quantity in Lagrangian perturbation theory. Lagrangian perturbation theory is an amazing branch of structure formation. Well, in fact, the very first nonlinear model for structure formation was developed in the context of Lagrangian perturbation theory. So it's really, an amazing, gigantic concept. But just because we have only 4 lectures, we're going to touch upon Lagrangian perturbation theory very little. But yet it's important to discuss at least the basics. And so the basic concept is this displacement field. Okay, it's a very simple concept. The displacement field measures how much a given particle moves from the initial position to the final position. Okay, so it's the difference between the final coordinate and the initial coordinate. Now we can evaluate what the displacement field is in linear theory. So we know that in linear theory, we know in principle velocity changes along the, let's say, fluid trajectory or along the word line. So it means that we need to integrate our velocity field that corresponds to particle that sits in xi. So this is really a label of a particle. And we know from linear theory we know that in cosmology we have adiabatic initial conditions. So for the adiabatic initial conditions, we only have basically a growing mode. And if we have a growing mode, the density and the velocity gradients are related. So the velocity will have a simple expression, which is a little bit non-local, but okay, this is fine. You have this 1 over Laplacian because of gravity. But in Fourier space, it's just 1 over k squared, so not a big deal. So we know exactly what the velocity is. Now we know how density changes with time. So in linear theory, just be delta 1. Now we can take this expression and plug it in our expression for the displacement and go to Fourier space. So this will be a little homework for you. Now you can nicely, even if you have this nasty growth factor here, but because you have dt, well, here I should maybe mention that t here is the conformal time. Okay, more on this later. Well, you can plug it here. You will see that it's going to take care of this nasty d plus, and you're going to end up with a very nice expression in the end. That the displacement field in Fourier space will look like this. So it will simply be given by the linear density field times, well, it will be gradient 1 over k squared. Okay. So now you can calculate the variance of the displacement field. So let's say I want to calculate the displacement field at the same point. So that will measure me, well, basically, let's say this quantity will measure a typical displacement of a given particle. So this quantity is very similar to the mass variance that we had before. Now it's just displacement variance. So we have this 1 over k. That's the only difference with respect to the mass variance. So we're going to get an expression that will look like this in linear theory. So we're going to get a dimensionful expression. And this mass variance, displacement variance is given now by an integral that is down by 1 over k squared with respect to the mass variance. And this 1 over k comes precisely from the extra 1 over k that is sitting, that relates velocity field and the density field in the adiabatic growing mode. Now, because of this factor 1 over k squared, we're going to find that the displacement variance actually is going to converge. So I can take my linear matter power spectrum for lambda CM cosmology, plug this into this integral, and I'm going to find an answer that will look roughly like 36 megaparsec over h squared at redshift 0, which naively means that a dark matter particle would travel on average 6 megaparsec over h during the entire age of the universe. So this is the typical displacement. However, okay, you see it's very nice that this integral converged, but can we trust this number? Who thinks we can trust this number? No one. Okay. It's the advanced school. Everyone is very advanced. Okay. Right. Can someone explain why we cannot trust this answer, even though the integral converged? Huh? Too easy. Right. Okay. When we're discussing the mass variance, you remember mentioned that, okay, we can evaluate something over a linear power spectrum only in the regime where we can trust linear theory, where a power spectrum is truly linear, right? So that means that this integral we can do only from 0 to k nonlinear. So even though this integral converged, it doesn't mean that it converged to the right answer, right? Because here the weight makes sense only up to k nonlinear. Now if you do this, you are going to find 32 megaparsec over h. So it will be, well, the typical displacement will be a little bit smaller, 5.5 megaparsec over h. Okay, it's not a big deal. And again, this is because this integrand, well, in this case, this integrand, even though you have this 1 over k squared, it's still, it's peaked for low case. So that's why in the end, it doesn't matter where your exact cutoff is sitting. But from conceptual, for conceptual reasons, it's important to appreciate this fact that any integrals that we're going to see for over linear quantities, they make sense only up to k nonlinear. Okay. All right. So the last. Good. So these are the important quantities that we estimated: the mass variance, the displacement variance, the growth factor. Are there any questions? Okay. If not, let me introduce the very last technical concept that I will need in my future analysis, which is the weak theorem. So as Julien described nicely in his lectures, we deal, in cosmology, we deal with the random fields, random stochastic fields, and just observations tell us this, that these random fields are linear. At high ratios, they are pretty linear. And here, in the context of large-scale structure perturbation theory, we're also going to build some sort of perturbation around the linear theory result, which is again is Gaussian. So it makes sense to discuss the different statistical properties of fields. And one of such property is called the weak theorem. Statement about the computation of correlators that involve more than more than two random Gaussian fields, right? So if delta 1 is the Gaussian random field, well, we know already that the 2-point function will give us the power spectrum. Well, another nice fact is that the 3-point function of these fields will give us 0. Well, unless we have primordial non-Gaussianity, which we're going to discuss later. But for Gaussian random fields, any correlator that involves an odd number of fields is going to be 0. And then the correlators that involve even number of fields will be split into a bunch of 2-point functions. So for instance, the 4-point correlator, it involves 4 fields. 2 fields make up a 1 power spectrum. So the 4-point function will have 2 times the power spectrum, okay? And in general, the weak theorem tells you that if you have a bunch of Gaussian random fields, phi, with some labels that I'm going to call I1 and IN, so their correlator is going to be given by a sum over ordered pairs of indices that I'm going to call Pij, and then products over different pairs in this ordered set of pairs. Pairs Pij. So again, this is just some formal way to state the same result. And in the context of cosmology, okay, we're only going to have, at one loop order, we're only going to have correlators of 4 fields and 6 fields. So it's pretty easy to write down how we're going to apply the weak theorem in practice. So in general, if we want to build these different order pairs, it's useful to start pairing fields in the correlation function by lines, right? So, okay. We need to sum over all possible pairings. Now, this is the first possible pairing. Now we need to sum it with some other possible pairing. Let's say now my first field is going to be contracted with the second field here, and these two fields. And the last possibility is that my first field is contracted with the second field, and then these two fields need to be contracted. All right. So it's very easy. Basically, in our context, if you want to apply the weak theorem, just you need to write down all possible, correlators, and write down all possible pairs that you are going to correlate to produce the power spectrum, right? So this is the weak theorem. So with that, I think that we covered all the necessary background to derive the EFT equations for dark matter. So are there any questions at this point? All right. EFT for dark matter. Now, in most of my discussions, I will not be distinguishing between dark matter and all of matter, just because, as we know, after a combination, dark matter and baryons, they form a single fluid, so it makes sense to talk about of um, all of matter in this sense. But strictly speaking, all the equations that I'm going to derive, they're true and only true only for this matter field, right? So for instance, we know that at small scales, then baryons, they have slightly different dynamics. We know that baryons live in galaxies, they have feedback, they produce stars and things like that. So on small scales, their dynamics will be slightly different and they will require a little bit of an extra treatment. But to a first approximation, we can always just, take all the baryons and sum them up with matter and say that everything is just matter, okay? So that's why I will not be distinguishing between matter and dark matter, but you should keep in mind that strictly speaking, the equations I'm deriving are true for dark matter only. Okay, so the usual story when we talk about, okay, again we have some, okay, we're going to have some scale separation. So the usual story of structure formation in cosmology is that we start with linear theory, where we treat dark matter as a pressurized perfect fluid, and by dark matter in this case, what we mean is a collection of particles, right, like WIMPs. And this collection of particles, truly, we can calculate its microscopic properties. We can calculate its pressure. It's going to be given by the temperature. It's going to be small. We can ignore it. It's fine. But however, when we now talk about dark matter in the context of, let's say, actual observations, what we see is that we don't see, individual dark matter particles. What we get to see on small scales are already the collapse objects formed by nonlinear clustering. So we get to see dark matter halos as some sort of fundamental unit where dark matter particles live. And then, so this picture obviously is very different. Let's say the gas of halos, or rather dark matter particles living in the halos gives you a totally different picture from just, usual gas of dark matter particles that just lives in the universe. So because of that, it makes sense to treat this particular situation slightly differently from what we normally do for linear perturbations, and more along the lines of the fluid, right? To say that, okay, we have some complicated dynamics, halos are complicated and nonlinear, it's fine. Let's just write down general picture of dark matter that could be sitting in the halos. Maybe this dark matter also is not even particles. Maybe it's represented by some sort of axion field, right? It has a microscopic dynamics different from the particles. So we don't want to think about this at all, right? We just want to write down, again, some emergent long distance description that would be independent on the details of the small scale dynamics. So this is the idea of the EFT of large-scale structure. So let's start now with derivation of the equations of motion following the path of the fluid equations. Well, basically, I'm going to derive the Navier-Stokes. I'm going to argue that the Navier-Stokes equation is an appropriate equation in this case. Okay, chapter 3, 3.1, equations of motion. Okay, well, first of all, I must apologize and say that I'm going to use tau as a conformal time. I wanted to switch to eta, but then I realized everything is going to collapse because I'm also using eta at the same time for something else. So sorry, Julian. So tau is going to be a conformal time. The formal definition is that we write down the Friedman metric in this form where it's conformally related to the usual flat space metric. And I'm also going to look at the perturbations inside the horizon. So well inside the horizon, k is much greater than h, so we can ignore relativistic effects at the leading order. In that case, it makes sense to derive the fluid equations in the context of the Newtonian cosmology, so Newtonian approximation. And I'm going to do so again by using the ideas from the usual fluid dynamics. So the density is going to satisfy the continuity equation. Continuity. And then the velocity field is going to satisfy the Navier-Stokes equation. That again I'm going to write down using the material derivative. Now the beauty of using conformal coordinates is that there will be no unknown factors of A lingering. So basically the continuity equation and the Navier-Stokes equation, they will take a look, well, they will take the exact same form as for the usual continuity and Navier-Stokes equation in the flat space. But then the difference, the cosmological expansion is introduced by the background quantities. So we're saying that the density of matter will have the background density satisfying the Friedman equation, time 1 plus delta. And the velocity field will have two components. It will have the Hubble expansion and the Pecure velocity field on top of that. And the only place where we have to deal with the, so, by plugging these things in at the background level, we're going to reproduce the Friedman equations. The only place where we have to deal with the scale factors is going to be the Poisson equation. So if I'm going to write down the Poisson equation for perturbed fields, so phi is my perturbed gravitational potential, delta rho is my perturbed density. So in order to reproduce the correct equation, I need to remember that delta is k squared, and any momentum should get redshifted, so I should replace this by k squared over a squared. So now if I do that, if I write down my perturbed equation like this is going to give me the right equation describing the dynamics of cosmological fluctuations inside the horizon. So you see that indeed this equation is exactly the same as what Julien wrote before. Okay, this is just a lazy way to derive the equations that otherwise follow from the rigorous theory of cosmological perturbations. Now, in that case, you can see that A will actually drop from this equation, provided that we also rescale Hubble. So we use something that is called the conformal Hubble parameter, which is A times the usual Hubble parameter. Now, the continuity equation, Navier-Stokes equation, and the Poisson equation form a system that describes a generic fluid, matter-like fluid during matter domination. Basically, these are the equations that we're going to solve. So the idea, again, is that we have something that has complicated dynamics on small scales. On large scales, we know that it should behave like dark matter. So those are the equations we're going to write down. And the information about the small scale properties is going to be encoded in the stress tensor, right? If the microscopic dynamics is that corresponding to the gas of dark matter particles, so this will be 0. But since we have halos on small scales, now this Tij, the stress tensor, is not going to be 0 anymore. So this is the key difference between the EFT of LSS and the linear theory of cosmological dark matter fluctuations. Right. Are there any questions? Okay, if not, let's go and try to solve these equations. Okay, they are so important, so I'm going to write them down neatly in one place for the moment. Okay. So we have already discussed that when I plug in this expansion into background and perturbations, the background equations will just reproduce the usual continuity and Friedman equations of matter-dominated cosmology. And now for the perturbations, for the perturbed quantities, I'm going to find the equations that will look like this. The perturbed continuity equation, and then I will have the perturbed Navier-Stokes equation that will look exactly like the Navier-Stokes equation in the flat space. The only difference will be is that, well, there will be this extra Hubble drag term that describes the redshift of velocities, right? The fact that the universe is expanding and the momenta are, the momenta of particles are going down. Then there will be an extra force produced by gravity. But it's also relatively easy to incorporate this force in the context of usual fluids. So it's not surprising. And then there will be a stress tensor. Finally, everything will be governed by gravity. Here I'm using omega matter as a function of tau, conformal Hubble, and delta. Okay. So this is the system of the fluid equations that you would write down for a generic, let's say, gravitating fluid during matter domination. And it just turns out that this first part, just like in the case of the fluid dynamics, will be more dominant for most of the evolution. So in some sense, this part that corresponds to the perfect fluid will correspond to the monopole. Monopole in the multiple expansion. And this last part will capture dipole and higher order terms. So in that sense, it makes sense to first try to solve these equations with tau ij set to 0, and then turn on tau ij and see what the impact of this. And this will allow us to compute next to lean order effects. Okay, so let's do this. Let's solve these equations in the first approximation that corresponds to the perfect fluid. So first approximation. Perfect fluid, tau ij is 0. Well, now you will see what my difficulty is with eta, because I'm going to introduce a new time variable I call eta, which is the logarithm of the growth factor. Now again, this is the exact growth factor that includes all the effects of the cosmological constant in it. And also it makes sense to introduce a new variable for the velocity gradient, which we know should be the only part of the velocity field that matters in linear cosmological perturbation theory. So just the velocity gradient that I conveniently divide by this f and h just to make up the units. Okay, so now what I'm going to do is I'm going to take my Navier-Stokes equation here. So it's for the velocity field. I can take the gradient of it, and then I will get, well, basically an equation for theta times f times h. So I'm going to take the gradient of this. And switch from TIV to minus theta FH. And then I'm going to take a Fourier transform of this equation. Okay, so there are several steps that need to be done. Change of time, change of variable, and the Fourier transform, but I trust that you can do it with your homework. And then you should be able to obtain the following answer in these new variables. All right, this equation looks a little difficult, but let me walk you through it. So you see the first part is just the linear part where every theta corresponds to the velocity field in this equation. And for the density field, once we apply this derivative here, we have the Laplacian of phi, and for this we use the Poisson equation, right? So this will explain the appearance of this delta here, and this factor 3/2 exactly corresponds to the 3/2 that you have in the Poisson equation, okay? So this part then is just simply follows from the linear terms, and now you have this convective derivative terms, v nabla v, and in Fourier space, this is going to be, a little complicated, so in general it will be a convolution integral with some, well, you see that it depends on the gradients and also the velocity field itself. If you want to express it through the density field, it will have a 1/k just following from the adiabatic modes, right? Or in other words, following from this definition that we have, right? So this will explain the appearance of this 1/q factors here. Okay? Well, I believe it should have 2 pi cubed. All right. So since I'm running out of time, probably I'll just stop here and I'm going to take questions, and then next lecture we're going to continue deriving the relevant equations and solving them. Yes, please.
Are the capital and lowercase thetas the same or the different?
This?
Yeah, is that a lowercase theta or is that a capital theta?
Okay. Right. So I'm going to use. Sorry. Let me do this maybe. Let me use only lowercase thetas for everything. Yeah. Okay. Yes. Yes.
When
Please.
obtain the velocity, the displacement, the velocity displacement field in the space, definitely like what people call the Dobson approximation is to trade and like I heard it's just
Yeah.
like I just skimmed through this stuff that
Yeah.
this approximation goes a bit beyond the things going on linear because of all these Dobson pancakes and stuff. If you know, if you comment on this, but if not, maybe it's just asking really a priori.
Yeah, that's right. That's right. Yeah, this is really a brilliant comment. So basically, what I drive you this expression for psi is the expression for displacement in a Zildjian approximation, where you're saying where you're using the Lagrangian picture to solve fluid dynamics that is equivalent basically to this picture, but in different variables. And then you compute the displacement field following from linear theory that basically will tell you that everything propagates kind of straight. Yeah, exactly. It doesn't change the direction. The only thing that gets changed is the amplitude of the velocity field. And indeed, now the standard story is that there will be a nonlinear transformation that relates the displacement field and the density field. So, and in the context of Lagrangian perturbation theory, people just say, look, I'm going to use linear displacement, but the full nonlinear transformation that relates density. So in this sense, the density field that you're going to get will contain nonlinear effects. And one of the, okay, so when you want to write down this relationship, what you're going to find is that 1 plus delta is going to be 1 over the determinant of something that will look like this d psi, well, d psi I over d qj, where q is the initial coordinate and psi is the displacement field, right? And displacement depends on the initial field. So what happens then is that this determinant can have 0 eigenvalues just as a result of evolution. And if all 3 eigenvalues are 0, you form like a cluster. If only one eigenvalue, if 2 eigenvalues are 0, so you have a string, which we call a filament. And if only one eigenvalue is 0, then you have the Zildjian pancake. So Zildjian was first to realize, oh, you have these different structures just following from this Lagrangian dynamics. Because even if you start from linear theory, you're going to generate all these things, caustics, already in this picture. Right. Okay. Thank you.